Okay, so we continue. I'm going to skip this last free body, right? But it is obviously, I take a bubble like this, just to conclude the BC, and we find that MP is equal to 0.4 pH minus P over 2x, and we find that NP is equal to 0.4 P. And we've completed everything. At this point, you are well advised to check your results by, for example, looking at the moment here on the top bar. If you evaluate the moment just before the hinge, what do you get? 0.4 pH minus 0.4 pH equal to 0. So that's correct, right? There's no moment just before the hinge here, or at the hinge. You look at this side, you find that if you take N, which is starting this way, as equal to 0.H, you also find that the moment just before the hinge on the right side is also 0 in this sketch, which is necessarily the case. Now, take these reactions off. Right? If we look at this side, the situation is different. On the right side of the hinge, there should be no moment whatsoever, right? Because it's a hinge and we are on the right side. So here, if we put N equal to 0.8H, we find a half minus a half, that's 0. However, if we look at the left side of the hinge where we have a 1 kip foot moment applied, the moment should be 1, right? So if we come here and we apply x equal to 0.8h, we would find a half plus a half, which is 1, and therefore all is well, right? So this is our P sketch, this is our one sketch, and everything has been completed. All we need to do now is just to write the answer. So you will actually, well, I will write the answer once and then you write the integrals, but it's clear that this is simply theta z on the negative side is equal to the integral left bar column 0 to h, contribution of bending MP, which is 0.4 py divided by EI, that's the curvature due to the load, multiplied times M1, which is 0.5 y over h, dy, because s, this is y is along the bar. That's the contribution to that coming from the bending of that bar. The contribution coming from the bending of the next bar, the horizontal BC, is the integral from 0 to 0.8h of 0.4 pH minus P over 2x divided by EI, which is the curvature due to the loading, multiplied by M1, which is 0.5 plus x over 1.6h ds, but s is x in this case because x goes along the bar, and so that is the contribution of bending from the second term. The next term is the integral from 0 to 0.8h, which is this bar, of MP, which is 0.4 p times h minus p over 2 times n over EI, that's the curvature due to the loading, multiplied times M1, which is 0.5 multiplied times nothing, minus n over 1.6h times dn, right? Notice that these two integrals are not the same. This is 0.5 plus x, this is 0.5 minus n, right? And finally, plus the integral from 0 to h, which is the last column, of 0.4 py over ei, which is the curvature, multiplied times 0.5 y over h times dy, which is the moment. These two integrals are the same. So I could have said 2 times this one, and that would have taken care of the 2 columns. But it's not 2 times this one, it's these 2 parts, right? So those 4 parts are the bending contribution to the rotation at C to the left side. We have, in addition to that, 4 more, which are due to the axial. So starting on the left side, we would have minus P over 2 divided by AE, which is the axial strain due to the axial forces, times N1, which is 1 over 1.6 h times dy from 0 to h. That's the contribution of the axial deformations to that rotation. Okay? Then we have the next bar. Integral from 0 to 0.8 h of 0.4 p over AE, right, times 0.5 over h times dx from 0 to 0.h. That's that bar. We've got 1. Wait a minute. What did I do here? I think I made an error. This one is this one. 0.4. No, wait a minute. 1, 2, 3, 4. No, I'm just doing this one now. Okay. So 0 to h, first one. Then 0 to 0.8 h. 0.4 p over AE times 0. No, I didn't make a mistake. So that's this bar. Now I'm going to the next bar. 0 to 0.8 h. This one, which is NP 0.4 p over AE, right? Times 0.5 over h times dn. Right? That takes care of the third bar, and then we have the last bar, and I have no room to write it. So since you have this copied, I'm going to erase the first blank and just say plus, right? Plus the integral from 0 to h for the last one of NP, which is P over 2 over AE, times N1, which is 1 over 1.6 over h times dy. There were terms like this, and this was theta c on the negative side. Right? So that's it. Now, you go over it. I've gone over it very slowly, so I don't think you should have any issue, but I suggest that you do it yourself without looking at what is here, and you get to this point. Then, in order to actually get the homework done, instead of h, there is some dimension in there. So you put the actual dimension. You can do it in h and then substitute at the end. That's what I would do anyway. And then there is an e, there is an a, and there is an I. So you will actually get some number. Okay? And that's it. So Okay. So let me erase everything here. Let me erase this part. And let me leave the 1 kip-foot moment there. If we had a different loading that was not the P load in the middle, but the question was the same, what is the rotation on the left side of the hinge, then the 1 kip load would be, it's the same, right? So different loads give different P's, but the 1 kip, the unit load moment, the unit moment case, does not change with the loading, it changes with the question. So let's ask the question for a different load, but not a load itself. Let's just say, what is the rotation on the left side of the hinge at C if what we have is a temperature change over bar BC? So if we have a temperature change over bar BC, somebody has to tell us what that temperature change is, right? So let's say that bar BC is a cross section whose depth is h bar. Okay? It doesn't really matter what the width is, but let's say it's b bar. So it's a cross section b bar by h bar, and we are going to say that the temperature change is that the temperature on the top of BC increased by delta T, and the temperature in the bottom decreased by half of delta T, where delta T is some temperature change. And so we have that temperature distribution. So now the problem is so much easier, right? Because when we have loading, we need MP and NP, right? In order to calculate the deformations, because the MP gives us the curvatures and the NP gives us the strains. But when we have temperature, the temperature already is the strains, so we don't need to do statics, we just need to transplant the information into the sketch. And so what we can say is that the phi in this bar is 0, the strain due to temperature is 0. In this bar is 0. The strain due to temperature is 0. On this bar is 0. The strain also axial due to the curvatures and the strains at the neutral axis are 0. So all I needed is on this bar, right? Now, from this sketch, we can see that the curvature, I gave a formula, but I don't think you should need to look at the formula. You just simply look at it and see, okay, what is the curvature, what is the slope of that line? So from the slope of that line, you can see that we have 1.5, oh, I'm sorry, that's the temperature distribution. The strains are just the coefficient of thermal expansion times the temperatures, right? So these are the strains. So you multiply the temperatures times the coefficient of thermal expansion and you get the strains. This angle is the curvature, right? And since it's a small angle, it's the same as the tangent or the sine or whatever you want, and you can easily see that it is equal to 1.5 alpha delta T divided by h bar. Okay? So we know that the temperature here produces a curvature of 1.5 alpha delta T divided by h bar. A question that arises now is whether that is a positive or a negative curvature. Well, that depends on what is the sign convention that we did on our 1 kip load. We can see from here that this temperature distribution, this is heating, right? So we are heating the top and cooling the bottom. The strains on the top of the section are positive, meaning the top is elongating and the bottom is shortening. Therefore, this is what's happening due to temperature, right? It's like this kind of bending, right? The temperature is increasing the fibers on the top of BC, reducing the length on the bottom, so it's doing that. Therefore, we have to see what was our sign convention when we did the unit load. And we can find that on BC, we used the sign convention for M1, which was also like this. So our M1 sign convention, you can check by going back to the free body diagram that we took M1 to be plus when it produced tension on the top of the bar BC, okay? Since that bending is the same as, since that curvature is the same as this one, then this is a plus. Had we used a different sign convention here so that the M1 was plus hogging water, then we would have had to say that this would have been a negative, right? We have to know that they are either on the same or on different. Just like when we do the P. So this remains plus. Now, the other thing that is needed is simply what is in the neutral axis the strain. Because that is the strain P, right? Once again, that strain P there is just a simple high school calculation using similar triangles or whatever you want, or I actually gave a formula. You can see, because this one is the big one and this one is the small one, that is going to be an elongation, right? And that elongation, in this case, in the middle, because the neutral axis here, we're assuming, is at half of h bar, is going to be positive. And so we would have that when you do the calculation, this, I'm sorry, that is not the strain. The strain is here, in the strain plot. Okay, so the strain EP proves out to be, in this case, 0.25 alpha delta T. Okay, this one is 1, that is 0.5. In the middle here, it turns out to be 0.25. Okay, now comes another question. Is that a plus or is that a minus? Well, for that we have to go back to our free body diagram of that bar BC, when we were doing the 1 kip load. And I can see from that free body diagram, I don't know how this looks, but anyway, from that free body diagram, that I assume the forces were compression to be plus. This strain right here is elongation, so it's in the opposite direction as what we assume for the N here. Therefore, this EP is a negative. That is, it has a different sign than that. N1 here is plus because it's compression, therefore this must be a negative. They have different signs. Of course, this could have been the negative, then this would have been the positive. The only important point is that they have different signs. And so we can transcribe here, and we have epsilon P due to temperature here to be minus 0.25 alpha delta T. And we're done. Because now it is a simple matter to say that theta z on the left side is the integral of the curvatures and the axial strains due to the loading in this case is temperature, and the unit load. So we go nothing in this bar, nothing in this bar, nothing in this bar, just in this bar. We have from 0 to 0.8 h, the curvature due to the temperature, 1.5 alpha delta T over H bar, that's the MP over EI term, multiplied times M1, which is 0.5 plus X over 1.6 H dx. Notice that it's not over EI again or something like that, right? There is no over EI. This is already the curvature. That's the bending part, and then plus the integral from 0 to 0.8 H of the axial part, which is minus 0.25 alpha delta T multiplied times 0.5 over H dx, and that's it, right? You substitute the values, do the integrals, and that's it. In this particular instance, I actually did, and I won't bore you with all the little elementary algebra, but the result is theta z minus, if I didn't make a mistake, is alpha delta T multiplied by 0.9 of H over H bar. This is the length of the height of the frame, this is the dimension of the cross section in the vertical direction, minus 0.1. That's what I got. Okay. Note that this formula does not involve E, I, or anything like that, or area. All right. So I have one thing left for today, and that is to do a simple example on the computation of the deformations due to temperature in a truss, and to remind you of the formulas that apply in the case of a truss. Okay. You have one in the homework, and here is an additional illustration. Remember that if you want, oh, by the way, in trusses, it doesn't really make sense to ask for the rotation at a point, because trusses are hinged, right? So there is no slope at any given point. When you have a truss, if you have a truss, right, like this, this A and B and C and D and E, right? And you have a load here or something, right? You cannot, it doesn't make sense to say what is the rotation at C, because there is no such thing as the rotation at C. There is a rotation on the left side of C and a rotation on the right side of C, but it doesn't make sense to apply unit loads, unit moments. So this truss, of course, will deform, and it could be that this, if I look at A, B, C, D, E, point B could end up here, while point C could end up there, and point D could end up here, and this is point E. So this is where B went, this is where C went, this is where D went, and so on. So it may be that you might be, but remember, all the bars in a truss after the loads, they are still straight, right? They're just connecting the joints. So if you wanted to know the rotation of bar BC, that would be equivalent to say, calculate the displacement of C, of B, calculate the displacement of C, and then see the tilt, right? So you might be interested in the tilt in some cases, but they always are, in the end, just calculation of deflections. What is the tilt of CD? Well, you calculate the deflection of C, you calculate the deflection of D, and then you see what is the tilt. So the point is really that what we're interested in is on the computation of deformations at joints in a truss. Now, when we calculate the deformation, we apply a unit load, right, at the point. And we have a term that comes in general, from bending, from shear, from axial. However, in a truss there is no bending. In a truss the bars don't have any shear either. So in a truss all we have is the integral over the complete structure of the axial contributions, and they are NP over AE, right, times N1 times ds, right? So this is the formula, and this means over the complete structure. Now, on a truss, I'm sort of repeating what I did in class, but just doing it again cannot hurt. So in a truss, right, it's mostly air. So this integration over the complete structure really means integrate over every bar, right? So that means that in a truss, over any bar, the axial force that is created by the loads is constant, right? This has NP on bar 1. This has NP on bar 7, and so on, right? So what we have is that these NPs over each bar are constant. And the same thing happens with the N1s. And therefore the deformations is not an integral, it's just a sum of NP over bar J, right? Multiplied over the area of bar J, divided over the E of bar J, multiplied times the N1 on bar J, and then the integral of ds over bar J is just the length of bar J, right? And this is from J equal to 1 to the number of bars, right? So this formula you've seen before, you've done homeworks I think on it, and so that's the deformation that you get on a truss if what you have are loads. Now, if instead of loads you have temperature, just like in the case before, this is the strain due to the loading. But for temperature, all we need is just to replace that by the strain in bar J due to the temperature, right? And so the formula for deformations on a truss due to temperature is just the product of the strains due to temperature times the N1 on bar J times Lj. So it doesn't get any easier than that. So only the bars where there is a temperature change contribute to the deformation. And therefore it is only necessary to calculate the N1s over those bars. Now in a truss we are not really interested on bending, only on axial. So when we talk about temperature changes in trusses, we are really only talking about temperature changes that are uniform. Now, you might ask, wait a minute, but I don't have any way to control the temperature. The temperature could have still be that my bar BC, let's say, had an increase in temperature delta T and a decrease in temperature delta T in the bottom like you did before, right? True, that may be possible, but the point is that we would only be interested on what is the strain in the neutral axis, in the centroid of the bar, right? So we would only say, all right, this is alpha delta T, this is alpha delta T, it's a linear plot, we go like this is all we care about, right? That's the E due to temperature. So it's only the epsilon at the neutral axis. In most problems, in books and texts and so on, they don't ever give you this not to confuse the issue, though in reality it might be like this. They always give you something like this, which is a uniform temperature change. Again, as far as the sign convention goes, if the temperature is a heating, then that means that the strains are positive, meaning elongation. No, not positive. The strains are elongation, and therefore N1 and this thing have the same sign if N1 is tension, right? And the opposite holds for compression. If this temperature is a cooling, and the N1 were compression, they would also have the same sign. Otherwise, if this is a heating and the N1 is compression, then they would have different signs, because the heating would produce an elongation and the N1 is producing a shortening, right? So that is it. That's the formula. And if you have loads in addition to temperature, then you just simply sum the two effects, right? So let's conclude by actually applying it in one particular case. So let's say we take a truss like this, right? Let's say that the distances from here to here to here are the same. We can call them L, L, and L. And let's say that the height is also L. We are going to label this A, B, C, D, E, F, G. We are going to say that bar EF is heated by delta T. So therefore there is a increasing temperature throughout the bar equal to delta T. Constant, uniform, as I said, is normally specified that way. And our interest is find delta at D in the vertical direction. So we want to find how much this point D moves in the vertical direction up or down due to a heating of bar EF through the length by delta T. Okay? So find delta D in the vertical direction. So first point is we recognize that this is a temperature problem. And since this is a temperature problem, all we're going to have in the P sketch are just the strains due to temperature. And since only bar EF is heated, we can just say that our strain here due to temperature is just alpha delta T, where alpha is the coefficient of thermal expansion for the material that is used to make bar EF, right? So alpha is the coefficient of thermal expansion of the material of bar EF, delta T is the heating of the bar. Since all other bars have no heating, then I don't really care when I apply, when I apply my unit loading, right? I only need the axial force over bar EF, because all the others will be multiplied times 0. So to calculate the bar force over EF, we simply do what? We could take, for example, this free body, right? And in that free body, I will do this. And so that free body would show a bar force here, a bar force here, and a bar force here, right? And this is the bar force that we want. So if we saw moments about point B, we will see 1 times 2L equals EF times 1L. And this is rotating clockwise and this is counterclockwise, So it's quite obvious that EF is equal to 2, kips in tension, right? Now, this is tension and this was heating, therefore those are the compatible signs, right? This is an increase, this is a tension, is an increase, not a reduction on length. Therefore we find that a delta D in the V direction is equal to the summation of N1 times the curvatures. So we only have this N1, 2, times alpha delta T times the length of this bar, which is L, and that is the answer to the problem of the deformation at D in the vertical direction due to a heating of bar EF of delta T. Okay? So, this concludes the material that will be covered. Well, I shouldn't say today concludes the material, I'm saying as of this moment, anything that I do after this moment that is new is not, meaning next class, is not in the midterm. But this stuff that we've done up to this instant is in the midterm. So, what you need to do, if you want to ensure yourself a good grade, well, I don't know if there is such a thing as ensure yourself, but let's just say that the responsible thing to do to be prepared is to make sure that you do these homeworks carefully, that you check that you know what you're doing, not that you can pattern match anything, but that you know what you're doing, okay? And if you have a little left time, then you can of course do others. There are many problems available everywhere regarding this kind of material, in the web and in books and in everywhere. So it's very easy. And practice makes perfect, and it also gives you confidence as you work on it. I'll close by saying, remember, write clearly, write large, use a lot of paper. All right? See you in a few days.